Okay, so here we are on this penultimate discussion or lecture. This feels like me talking for a while. So I guess a couple things. I did get exam 3 graded, so those grades are posted. The corrections assignment is posted. I think those are due Saturday. Let's see, what else? What else? Again, the final exam practice exam is posted. So practice for the final exam. There are 2 new equation sheets for that exam. They are posted and have been posted for a while. I'll also include some thermal data for water, which is a little table. And you can use any of the other equation sheets for that exam as well. That'll be available at the latest Friday at 8 a.m. Although I've entered almost all of it. So once I get it all entered into the computer, I'll open it up. So you could take it earlier if you were so inclined. So let me ask, do you guys have any questions? No. Were you wondering if the Iron Man mask on my wall over here, if the lights, if the eyes light up? If you were wondering that, the answer is yes. Although now it's like front lit. Can you see that? I can't wear it though. It's just like it's a nightlight, basically. I can't get back on. If you weren't wondering that, now you know. So, okay, that was a Goodwill find. Because in the toys, what else are you gonna do? Okay, so what have we talked about? We've more or less finished chapter 13 yesterday. And I did post 2 videos for chapter 14 today. There'll be 3 more videos for tomorrow, although I'm not testing 2 of those concepts. So let me lay that out clearly right now. In chapter 14 is sound. All right. I may talk about, well, here, let me just bring up I'll just show you this. I need to share this screen. All right, because this, I want to talk about everything in here, but just feels weird to talk about it on Thursday and then assign you a final exam that could also be available on Thursday. So let's see, constructive, destructive interference. I will talk about. I'm gonna post a video about it. We may do some example problems, but I'm not going to test it. All right. The idea that sound is a longitudinal wave, that you should be familiar with that. All right. The idea that you can change the speed of sound. This equation, this V equals the square root of gamma RT over M. I'm not holding you responsible for that, meaning I'm not asking you to do any math with it. But just be aware that sound is a wave in air. And the only way to adjust the speed of sound is to adjust the medium, right? So you could ask, so a tuba and a flute, right? Both play in a field, in an open field. That sounds creepy, but not if you practiced marching band in Kansas. So you have a tuba and a flute. You could ask, they both play on the opposite end of the field. Which sound reaches the other end first? And the answer is, well, they reach at the same time, because the speed of sound does not depend on frequency, right, or wavelength. The speed of sound depends on the medium, and the medium's the same for each of those. All right, it's the same air at the same temperature. I did want to suggest this, though, that if you have an instrument filled with air at a different temperature, that changes its resonant frequencies. So if you've ever played in a band and you've heard them, or you yourself have warmed up, right? So warm up has more than just like your lips. So I played the trumpet. So when I warm up, I'm warming up my my lips, but you're also warming up the instrument, like literally warming up the air in the instrument, because a cold instrument and a warm instrument are going to be tuned differently because the speed of sound is different for them. Very similar to if you breathe helium and talk, right? So instead of, so we could zoom into that. Can we zoom into that? I would love to zoom into that. There. So what I'm talking about are these two variables, temperature and molar mass, right? So temperature is what changes when you are warming up your instrument. Molar mass is what changes when you breathe helium. All right, both of those are changing the speed of sound, so that's why you have to warm up your instrument. Okay, let's make that go away. So what was I doing? Basically, I'm recovering sound, right? So one of the videos for today is introduction to sound. The other one is about intensity and sound level, and we'll get to that. So interference is useful to talk about. In fact, talking about it now really helps when you guys talk about light in 202 in like 3 weeks or something. Oh, come on. So I feel compelled to talk about that. Intensity and sound level, those you are responsible for, all right, which is why they're not grayed out. But the Doppler effect, again, I would be remiss if I did not talk about the Doppler effect when we're talking about sound. But I'm not going to hold you responsible for it, meaning I'm not going to ask you to do anything on the exam. There may be some homework problems, but I think they're probably extra credit. Standing sound waves, you are responsible for, right? Again, that's why it's not grayed out here. But standing sound waves are very similar to standing waves on a string. And we'll go back and talk about that a little bit, and then we'll do some examples for sound. And beat frequency, we may talk about that. Let's see. So I talked about 2 of these tables for, 2 of these tables in the videos for today. 15.1, you'll notice this isn't chapter 15, this is chapter 14. Well, I took this table from another text. But that's the speed of sound for various things, right? So the speed of sound is indeed a function of temperature. It's also a function of what the air is made of, right? So if the gas is helium, speed of sound is a lot faster. Trying to decide whether to talk about intensity and sound level. Maybe I'll talk about it quickly. I think I did all the examples that I had for that. Just to say, so intensity is power per unit area, right? So when a wave leaves a source, it spreads out. So a way to quantify how far it is spread out is to talk about intensity, right? So the further away you get from a source, if it's not a source that's linear, like so a laser pointer is a pretty much unidirectional emission, right? But that spot does get a little bigger, but not like a normal kind of flashlight, right? So the intensity for, say, a flashlight gets smaller as you get further away. In fact, it falls off as a 1/r², which you saw in lab if you've already had it, or you will see in lab today or tomorrow. But for sound, the human ear is sensitive to a very, very large range of intensities, right? So the quietest sound you can hear is probably 10⁻12 watts per square meter. The loudest sound that won't hurt you is something like 1 watt per square meter. So that's 12 orders of magnitude. So the way that we deal with that range, if you're going to talk about it often, right? If you want to talk about loudness, we actually define loudness as a thing, right? It's a log base 10 of the intensity scaled by what we want to call 0, and then you multiply by 10 decibels, right? And I gave that equation in I'll write it up here quickly. So sound level is 10 decibels, just sets the scale, times a log base 10 of an intensity divided by I naught. And I naught is just this number right here. Right, and what that does is it changes our scale from 10 to the minus 12 to about 1 to 0 to 100-ish, right? 100 or 120. Okay, so when you see something in decibels, that's just a nicer way of talking about intensity, really. Okay, questions?
So is the B letter, is that like a variable and the units are decibels?
Absolutely, yes. So this B letter is, in fact, the Greek letter beta. I don't think I gave it a big enough tail, though. But yeah, that's just intended to be beta. And the dB, that's a decibel, right? So a decibel.
Okay.
So the units for for sound level is decibel, but the unit that is meaningful, or the unit that that you can make from other SI units, is the watt per square meter, right? A decibel is not made up of other SI units. It's just a number that we chose to set a scale. Other questions? Cool. So like I said, I did a couple examples. I did this one and then it erased all of my work, but it's in the video. I also did this one, so I'm not going to redo those. This is for standing sound waves. That's for tomorrow. That's for tomorrow. That's for tomorrow. Okay, so I want to go back to chapter 13 and talk a little bit longer about standing waves on a string, and then I'll segue that into standing sound waves. Is that really what I want to do? Because I think standing sound waves is a video for tomorrow. Let me see. Let me load up my plan. Where did that go? Yeah. Yeah, I mean, that's fine. I think that's okay because I don't have other things to talk about unless you have a litany of questions, which is totally fine. So let me remind you of standing waves on a string. And again, you can make these yourself. You're looking at that. Now you're looking at this. Right? By just like tying a rope or a slinky. Slinkies work great for this. As long as you don't shake them too hard. If you do, you'll get like kinks in them. That's unfortunate. But you can just like tie a rope, particularly if it's a little longer, to one end, right? And then hold the other end in your hand and shake it up and down. And you'll notice if you shake it faster and faster, you can access these modes. So these modes of oscillation only happen at specific frequencies. And those frequencies correspond to specific wavelengths. And the wavelengths you can read directly off of this plot. All right, so I showed this yesterday. Let me see if it's still up. No. Standing waves, GIF. Do you guys say GIF or GIF?
GIF. It's GIF.
GIF.
Guess it depends on how much you like peanut butter. Okay. So here's the picture, right? So these are the kinds of waves that you could make on a string. And in fact, I love doing a lab based on this. You can use some elastic cord, and you can actually change the tension in the cord to get different modes. You can use a fixed frequency. You can plug it into the wall and get you end up getting 60 hertz because of a rectifier in the circuit. But yeah, you can use a fixed frequency and change the tension to change the wave speed, and then you can get different modes of oscillation, basically different wavelengths. So I'm not going to rederive. Let me go back to this equation, but you can see here, for a standing wave on a string, lambda sub n, so this is the wavelength for these modes, right? So the fundamental and the first harmonic and the second harmonic, well, the first harmonic is the fundamental. The second harmonic, the third harmonic, those are just different ins. Sometimes I've used m in the past. You may see me change between n and m. They're just integers, all right? So that's what that n is. Lambda 1 is 2L, lambda 2 is 2L over 2, or just L. Lambda 3 is 2/3 L. And you can read that directly off of these pictures, right? So lambda 3, the length is the whole bit here. Let's go back to purple. Right, so this is the full length of this string. That's not changing, but the wavelength is changing. The wavelength is 2 of these lobes, right? And I talked about why that is in the video. So 2/3 of L is the wavelength. You can kind of see that, where there are 3 half waves in one L. All right, yeah, so let's do an example. Again, lambda sub n is 2L over n. Remembering that V equals lambda F, and you have to match up the n's there. It has to be lambda 1, F1, lambda 6, F6. If you multiply like lambda 2 by F3, you'll get a number that has units of meters per second, but it's meaningless. It doesn't have any bearing on the system. And you can use V equals lambda F and the lambda sub n equals 2L over n to calculate the frequencies as a function of n, and you see that it's just integers times the fundamental frequency, right? So if 100 hertz is your base frequency, you'll also see resonance at 200 hertz and 300 hertz and 400 hertz, which is kind of cool. Okay, so let's do another example. Here's example number 11. Says an experimenter finds that standing waves on a string occur at 24 hertz and 32 hertz, but not in between. The question is, what is the fundamental frequency? And sketch the standing wave for the 32 hertz. Okay. So what do we know? Well, we know that at a frequency of 24 hertz, I get a standing wave. And at a frequency of 32 hertz, I get a standing wave, but I don't know which waves those are, right? I can't just call that 1 and 2 because I don't know that. I do know that they're right next to each other. They're consecutive because there's nothing in between. So I could call this F sub m and F sub m plus 1, right? Because that's what I know. I know that they're consecutive. So the question is, what is the fundamental? So what is F sub 1? Right, and then I also want to sketch for the 32 hertz wave. Okay, so what do I know? I know the equation F sub n is n times F sub 1. So what does that mean for the difference between F sub n plus 1 and F sub n? What is that difference? Well, F sub n plus 1 would be n plus 1 times F1, and then it's minus n times F1. So do you see the difference between consecutive frequencies is the fundamental frequency? The difference between consecutive frequencies is the fundamental, right? And well, yeah, I don't think I'm going to belabor that point. So what that means is that F1 should be 32 hertz minus 24 hertz, right? What is that? I'm asking, is it 8? I don't know, my brain is fried. 8 sounds right to me though. Good. I can still do mental math. Great. Great. Questions about this? Does this make sense, you guys? So the next part of the question is sketch the standing wave pattern for the 32 hertz wave. So to sketch the wave pattern, I need to know which harmonic it is, right? I need to know what in is for that wave, right? Because we go back to this picture, this picture, right? And n equals 1 gives me this kind of pattern, n equals 2 gives me that pattern. This is kind of a mess. Let's make some of this stuff go away. Not all of it, just some of it. Right, so this is what I'm asking is, what does the picture look like for the 32 hertz wave? So I just need to know which in is 32, right? Okay, so we go back here and we say, well, f sub n equals n times f sub 1, and f sub 1 now equals 8 hertz. So for the 32 hertz wave, what is in if f1 is 8 hertz? Well, 32 divided by 8 gives me 4. So n equals 4 for the 32 hertz wave. All right, so what does the n equals 4 pattern look like? Well, n equals 1 is a single lobe, n equals 2 is 2 of them, n equals 3 is 3 of them, and n equals 4 must be 4. So that's a terrible sketch of the standing wave for this, for 32 hertz. Does that make sense? So if on a test, maybe the last test in this course, if you had a question that that gave you an image like this, and maybe, I don't know, maybe like the frequency or something, you can actually use this picture to tell you some information, right? You can use this picture to tell you which in you're looking at. Okay, let's move forward. Do you guys ever notice when you microwave stuff that there are hot spots and cold spots? Do you know why that is? A microwave oven supports standing microwaves, right? What is a microwave? It's just light, right? It's just light of a certain certain frequency and wavelength. And the wavelengths for microwaves are on the scale that they form standing waves of like n equals single integers, right? Not crazy high integers in the size that is your microwave. All right, so the cold spots are because of nodes, right? A node is a place where the electric field isn't changing at all. An antinode is where the electric field is changing a lot. That's going to be a hot spot. So if you wanted to know, like, where are the hot spots and cold spots in my microwave oven, you could just microwave a casserole, right? Put a whole casserole dish in there. Don't turn the turntable on. The turntable is to prevent the cold spot, right? So let's see here. So measurements of the temperature across the oven show that there are cold spots at each edge, which makes sense. And maybe you'll see this in physics too. The E field in a conductor is always 0. So the E field at the walls is definitely going to be 0. But there are also spots in the middle that have nodes. There are 3 spots. So 1, 2, 3. Right? So then the standing wave in our oven looks like this. Right? That's what it looks like at one time. And at another time, it looks like this. And so, yeah, this has 3 nodes in the middle. And the microwave wavelength is 12 centimeters. So we're given that lambda equals 12 centimeters. And I want to know, what is the length of this oven, right? What is this length? Well, I can pretty much read that directly off of this, right? I can say one wavelength, let's use a different color, is 2 lobes, right? That's one wavelength. So there are 2 of them here. And if the wavelength is 12 centimeters, then the length must be, in this case, I don't want that picture there. Come on, please. Perfect. 2 lambda, in this case, it's 24 centimeters. So that's how wide this microwave oven is. Does that make sense, you guys? The other way you could do this is lambda sub n equals 2L over n, right? If you're not comfortable drawing this picture and kind of like arguing from your gut, you can argue from an equation, right? Neither one is more right than the other. It's just how you feel comfortable thinking, right? So sometimes if I'm lost on a problem, if I haven't developed intuition for it yet, I'll start with what I know is true, which are the equations, right? Because I trust the derivation. In this case, I did the derivation, so I might not trust it as much, but that's fine. I do trust this one. So lambda sub n equals 2L over n. I know that this n equals 4. For standing waves where there are nodes at both ends, it's the number of antinodes that is the n. The easiest way for me to argue it is to say what I did up here, which is one lobe like this is n equals 1. 2 lobes is n equals 2. And then it's pretty clearly the number of lobes, right? So this has 4 lobes, so it's n equals 4. Confused myself by moving my controls up there. Okay, so then that lets me plug directly into this. Lambda sub n, we're given that the wavelength is 12 centimeters, is 2L over n is 4. Then I can solve this for L. So this is the same as L over 2. I multiply the 2 over and I get L equals 2 times 12, which is 24. Good. Solved it 2 ways, got the same answer. Feel pretty good about that. Okay. So this is standing waves. Standing waves on a string. And this last example is a microwave, but it's the same math. What about sound? What about sound? Well, let's talk about sound. We have 10 minutes. This is something I have planned for a video for tomorrow. Maybe I'll just introduce a little bit of it. Yeah, I'll just introduce the first bit and I'll introduce the second bit in the video for tomorrow, because there's enough information here to do that. So sound is a pressure wave. Let's do a new thing with like sit there. Okay. So what do I need to have a standing sound wave? Well, we need some kind of container, right? We're used to, like in music, thinking of most wind instruments are some kind of tube, right? Brass instruments are tubes that you vibrate one end. Woodwinds are the same sort of thing, right? You're vibrating one end basically. But you could think of something as simple as, have you guys seen boomsticks? Dare I Google? We're gonna try it. It's not like I'm gonna post this on the internet later. Oh, hey, let's try it. Not that.
Like the things they use in soccer, so maybe boomsticks for soccer, like the
Yeah,
crowd.
Maybe it's one word. It's the toy. Yeah, no. Thundersticks, inflatable boomsticks. Nope. You know what? That's fine. I've Googled, I've tempted fate enough. I almost clicked on images, but let's not. That's the last thing I need. I'll find a video of something of what I'm talking about. Suffice it to say, you can set up a standing wave in something like this. Actually, I tried to have us do a lab. I think I've mentioned this, where this is water in an empty 2-liter bottle. Right, you can make sound from this, and if you pour out some of the water or put more water in, you can change that frequency. That's the fundamental frequency. But there are more frequencies that will live in this thing. But we have to think, so what does a standing wave in a tube like this look like? So this is an open tube. So the pressure at each end, see, I think I drew that wrong. The pressure on each end is a fixed thing, right? Because each end of this is open to the atmosphere. So the pressure here is P atmosphere, and the pressure here is P atmosphere. Right? So inside of this tube, I can set up a standing wave. Here's what I'm arguing. If the open end is always at atmospheric pressure, that's a node, right? Because remember, pressure wave sound is basically a variation in the pressure in air, right? So it's not allowed to vary here. So this end is a node and this end is a node. So if I have an antinode in the middle, that will be my fundamental. That's going to look like this, right? And the next highest standing wave, make this go away, in this open tube it's still going to have a node at each end, but it'll have a node in the middle. So it'll look like this. And the next highest standing wave will have 2 nodes in the middle. So it might look like this. This should look familiar. If it'll ever catch up. There. This should look familiar, right? This is just like our standing wave on a string. So all of these no. This is just nodes and antinodes, right? I'm labeling where the nodes and the antinodes are. So this is n equals 1, n equals 2, n equals 3. And if I let the length of this be L, everything that we built for standing waves on a string, all of the math that we built for that will work for this too, right? So lambda sub n is 2L over n. V still equals lambda n times F sub n, and F sub n is going to be n V over 2L, or n times a fundamental frequency. All right, so what I expect for a musical instrument that can be modeled this way, what I expect for it is for the length of the instrument and the fundamental frequency to be related in this way. So the speed of sound is like 343 meters per second. So then the length of the instrument is going to dictate the fundamental frequency. So this is kind of like a flute, right? A flute is open on the far end. Yeah? So let's see, does that track? The shorter, yeah, that tracks, right? So let's draw 2 instruments. Come on, show up. So the top instrument here, I intend to be the flute. And the bottom instrument is a piccolo, which I probably spelled wrong, but I don't care. Can you see the piccolo? Has it shown up yet?
No.
Why is this taking so? Yep. Okay. We lost connection. That's fine. I'll reconnect. Okay, so there's my flute and there's my piccolo. So a flute is longer than a piccolo, right? So if L is longer, I'm dividing by a bigger number, right? So the fundamental frequency for a flute is going to be smaller or lower than the fundamental frequency for a piccolo, right? Piccolo is smaller, so I'm dividing by a smaller number. That makes that fundamental frequency higher, right? And that tracks, right? If you've ever heard a piccolo, it's a lot higher pitched than a flute. Okay, so there's another type of instrument. I'm just going to mention it, or another way to set this up, and I'll do the math in the pre-lecture video for tomorrow. So instead of having an open system, so it's open on one side and open on the other side, I could have an open closed system. All right, most brass instruments are modeled as open closed systems. All right, so what does that mean? Well, this side is still always a node, but this side is always an antinode. All right, why would that be an antinode? Well, because the air is rushing toward it and then rushing away from it. So it's going to be a high pressure and then a low pressure and then a high pressure and then a low pressure. That makes that's an antinode, right? Whereas this side is always P atmosphere. That's a node. So what that's going to look like, the standing waves, well, I'll just tell you, the standing waves in that look different than the standing waves in the open system. So we're going to have to build a different set of math for that, and that makes the fundamental frequency different as a function of length, and it makes the harmonics look different as well. So you have that to look forward to. That's a video for tomorrow, and we'll do some examples for that probably in class tomorrow. So let me ask before we close, are there any questions? No questions. Okay. Cool. So so let's call it good. Like I said, I will post 3 videos for tomorrow. One will be the standing sound waves. We'll do interference, and I'll do the Doppler effect. Okay, so I'll see some of you in lab. There is no more discussion, right? So there's no discussion tomorrow, and there's certainly no meetings on Monday. And otherwise, I'll see you guys in lecture tomorrow. So thanks for your attention.